Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be back. We've got a massive topic today.
We really do. I want to start by having you, the listener, imagine a scenario. You're standing in a reinforced bunker looking through 6 inches of ballistic glass.
Oh, this is the jet engine story, right?
Yeah, exactly. So you're looking at a $50 million prototype jet engine bolted to a test stand. The countdown hits 0. The igniters fire.
And that turbine spins up to what, like 30,000 RPMs?
Something crazy like that, yeah. And for exactly 4 seconds, it is just this symphony of perfect thermodynamics.
Right.
But then a high-frequency vibration starts in the compressor stage.
Which is terrifying when you're dealing with those speeds.
Completely. Within 2 seconds, the vibration amplifies, the titanium blades shatter, and the engine literally tears itself apart in a catastrophic hail of shrapnel.
Just millions of dollars gone in an instant.
And months of forensic analysis later, they trace the failure back to a seemingly inconsequential decision. A junior purchasing manager decided to substitute a specific mounting spring.
Right, with a visually identical but slightly cheaper alternative.
Exactly. That single spring altered the tension on a bearing by just a fraction of a millimeter. It shifted a resonant frequency just enough to destroy half a decade of engineering.
It's wild how fragile these complex systems actually are when you peel back the layers.
It really is. So today, we are diving deep into the invisible architecture that prevents that specific nightmare from happening. We're dismantling systems engineering.
Right, and we'll be getting into Nampio-Su's axiomatic design, plus the really rigorous mathematics of critical parameter management.
Because our mission today is to understand how we actually orchestrate the interactions between hard science, massive human organizations, and just unforgiving physics.
And we have to do that to build complex systems that actually work,
Exactly. So to kick us off, the premise we really have to start with is that large-scale engineering failure is rarely a failure of physics.
Yeah, or a lack of technical knowledge.
Yeah.
It is almost always a failure of cognitive capacity.
Which sounds a bit abstract, right? I mean, systems engineering exists fundamentally as a debiasing mechanism.
It is. It's a highly structured management technology designed to counteract the severe limitations of the human brain when we're faced with overwhelming complexity.
Because we just have an incredibly restricted working memory.
Oh, absolutely. We simply cannot simultaneously hold the thousands of interacting variables of an aerospace platform in our active consciousness.
Or a global supply chain, or a massive software backend, for that matter.
Exactly. When a human engineer, or even a whole team of engineers, is subjected to a cognitive load that exceeds that biological threshold, they default to these deeply ingrained psychological heuristics.
They start looking for the mental exit ramp.
Yeah, they fall back on what Herbert Simon called satisficing.
Satisficing. Okay, let's unpack this for the listener. That's a portmanteau of satisfying and sufficing.
Right. It means searching for a solution that is just, well, good enough.
I always think of it like trying to cook a 5-course meal in a messy kitchen without a recipe. You might satisfice and serve something edible, but it won't be a masterpiece.
That's a great analogy. If I'm trying to route a complex wiring harness through a dense automotive firewall and I have 50 other components competing for that physical space, I don't naturally seek the mathematically optimal route.
You just look for the first route that doesn't immediately hit the steering column.
Exactly. And I lock it in. I grab the solution that makes the immediate pain of the problem go away.
Even if it creates a total thermal management nightmare for the exhaust team downstream.
Precisely. And the danger of satisficing in unstructured environments is that decisions inevitably skew into 2 really catastrophic categories.
Which are agenda-dependent and intellect-limited, if I'm remembering the source material correctly.
You got it. Agenda-dependent decision-making happens when the technical vacuum is filled by organizational politics.
Ah, right. So the subsystem that gets the optimal packaging space isn't the one dictated by physics.
Nope. It's the one controlled by the loudest vice president or the most aggressive department head.
Which is just a terrifying way to build an airplane or a car.
It really is.
Yeah.
And then you have intellect-limited decision-making. That means the architecture of the system is constrained by whatever specific variables the lead engineer happens to understand best.
While ignoring the domains they are less familiar with.
Right. Like if a software architect is a database specialist, the entire system morphs to optimize data storage.
And that could potentially cripple the user interface latency or something else entirely.
Exactly. So systems engineering forces a rational, objective aggregation of facts and values before a single piece of metal is cut.
Or before a single line of code is written. It demands that we define the problem through exhaustive requirements engineering.
Yes. And I want to dig into the semantics of requirements engineering, because this isn't just about writing a nice wish list on a whiteboard.
Oh, not at all. The language is terrifyingly pedantic.
It has to be.
Yeah.
It operates almost like a hybrid of physics and contract law. When we look at the source documents, the hierarchy of language revolves around three specific modal verbs.
Shall, will, and should.
Right. If I write, the structural housing should withstand a 50G impact, I haven't actually engineered anything.
You've just stated a preference.
Exactly. Using should in a formal requirement introduces lethal ambiguity. Should designates a goal or a non-mandatory provision.
It essentially tells the contractor that this is a desired attribute, but if it proves too difficult or expensive, they can just abandon it.
Right. They are contractually and technically permitted to just walk away from that goal.
Yeah.
The true cornerstone of the discipline is the word shall.
Shall. It feels so archaic, but it carries so much weight here.
It does. When a document states, the system shall execute the failsafe protocol within 200 milliseconds of power loss, that is a legally binding, mandatory provision.
It must be verifiable through specific testing criteria, right?
Yes, and it must be necessary for the core function of the system and physically attainable. If a single shall statement is unfulfilled, the entire system is classified as non-compliant.
Wow. And what about will? Where does that fit in?
The word will is merely a declaration of purpose or a statement of fact regarding the future operating environment.
Like saying the vehicle will operate in sub-zero Arctic conditions.
Exactly. It provides context, but it doesn't assign a specific testable engineering burden to a specific component.
Okay, so let's trace how those shall statements actually propagate through a massive organization. You have thousands of these binding requirements.
Right, you can't just dump them on a single team's desk. It would be chaos.
So the source material outlines the V model of systems engineering, which fundamentally maps the division of labor against the division of engineering knowledge.
Yes. We start at the top left of the V, looking at the entire abstract system, and we move downward, decomposing the problem.
And decomposition is basically the deliberate fracturing of complexity into manageable, isolated domains, right?
Exactly. Take the automotive powertrain example from the texts. At the highest level, you have a vehicle-level requirement.
Like, the vehicle shall achieve 0 to 60 miles per hour in under 6 seconds.
While maintaining specific emission standards, yeah. And no single human can design a complete engine from scratch to meet that.
So the systems architecture defines an organizational architecture. This is a practical application of Conway's law, isn't it?
It is. Conway's law states that organizations design systems that mirror their own communication structures. Systems engineering uses this intentionally.
So we establish a director of powertrain engineering, and below them, we create strict boundaries.
Right. We assign a chief engineer entirely to fuel systems and a completely separate chief engineer to exhaust, cooling, and mounts.
Wait, but if we are rigidly siloing these teams, how do we avoid creating a fractured product?
What do you mean?
Well, if the fuel systems engineer is only looking at their specific shall statements regarding injection pressure, and the exhaust engineer is solely focused on thermal dissipation, don't we end up with components that work perfectly in isolation but fail spectacularly when bolted together?
The classic, the operation was a success but the patient died scenario.
Exactly.
The integration doesn't happen by accident. It is managed through rigid baselines. The left side of the V model moves through 3 distinct phases.
Okay, let's break those down for the listener. First is the functional baseline, right?
Yes, which defines what the system must do functionally, independent of any physical hardware. Next is the allocated baseline.
And this is the critical intersection I was asking about, right?
Exactly. At the allocated baseline, we allocate specific functional requirements to specific physical subsystems. But more importantly, we explicitly define the interfaces between them.
So the systems engineering team dictates exactly how the fuel system will physically and digitally interface with the combustion chamber.
Right. The fuel engineer and the exhaust engineer don't need to coordinate their daily activities because the systems architect has already negotiated and hard-coded their boundaries.
That makes a lot of sense. And finally, we reach the product baseline at the bottom of the V.
Yes, which consists of the detailed build-to-print specifications. the actual geometric tolerances and material choices.
And once we hit the bottom of the V, where the individual parts are actually manufactured, we pivot and start moving up the right side of the V.
Right, this is the verification and validation phase. We test the fuel injector against its product baseline.
Then we integrate the injectors into the fuel rail and test the subsystem against the allocated baseline.
Exactly. We drop the engine into the chassis and validate the entire vehicle against the functional baseline. It is a systematic reconstruction of the complexity we broke down on the left side.
So the discipline of the V model prevents the integration phase from becoming a chaotic discovery phase.
Precisely. In an unstructured project, engineers just slap components together on a test stand and discover how they interact.
Which usually results in endless, expensive redesign loops.
Yeah, it's a nightmare. By rigidly controlling the requirements and interfaces on the downward slope, the upward integration slope becomes a predictable confirmation of established physics.
Rather than a desperate troubleshooting exercise. But let me present a philosophical objection to this.
Okay, let's hear it.
The rigid adherence to top-down decomposition, the obsessive tracking of shall statements, the siloing of engineers into microdomains, this sounds like the antithesis of innovation.
How so?
Well, we often romanticize engineering as a blank canvas, you know? Like a skunkworks garage where brilliant minds organically invent the future.
Sure, the lone genius trope.
Right. Doesn't this heavy-handed management technology essentially lobotomize the engineering process, turning highly educated designers into bureaucratic box checkers?
I get why you'd think that, but the romantic notion of the unconstrained genius in a garage is largely a myth when it comes to highly complex, safety-critical systems.
Really? Total freedom doesn't work.
Total unconstrained freedom in a multivariable environment doesn't foster innovation, it paralyzes it.
Oh, because there are too many unknowns.
Exactly. An engineer tasked with designing a fuel pump without defined constraints will spend 80% of their time trying to guess what the electrical team might do with the voltage supply.
Or what the packaging team might do with the physical space.
Right. The rigid boundaries established by the systems architect actually liberate the detailed designer.
By guaranteeing the inputs and outputs.
Yes. By saying, you will receive exactly 12 volts here, and you must deliver exactly 40 psi of pressure there. Within this geometric envelope, the systems engineer creates a protected sandbox.
Oh, I see. So the detailed designer is now free to apply all of their creative energy toward optimizing the internal mechanics of that pump.
Knowing with absolute certainty that their brilliant solution won't break the broader system. Constraints act as the scaffolding for deep, focused creativity.
That's a profound way to look at it. Okay, so we have established how systems engineering manages the human element to prevent bad decisions.
Right, but managing human cognitive limits is only half the battle.
Exactly. A perfectly managed, beautifully documented engineering organization can still produce a terrible product if the underlying design decisions are scientifically flawed.
Which transitions us into the realm of pure design theory.
So, is there an underlying scientific law that dictates what actually constitutes a good design decision? Can good design be reduced to mathematical laws?
For decades, design was treated entirely as an art form or a heuristic practice based on trial and error. You built it, you tested it, you broke it, you improved it.
But Nam-Pyo Su rejected that, right?
He did. Nam-Pyo Su, a visionary professor at MIT, rejected this paradigm entirely. He argued that just as thermodynamics has fundamental laws governing energy transfer, the process of design must have fundamental axiomatic truths.
Truths that dictate success regardless of the specific engineering discipline.
Exactly. Through rigorous analysis of successful and failed systems across various industries, he distilled the entire universe of design theory down to two foundational principles.
Creating what we now call axiomatic design. So before we dissect the axioms, we need to map the territory.
Right. Su structured the design universe into four distinct domains. It is essentially a framework for translation.
You start in the customer domain, which captures the customer attributes. This is the voice of the end user, which is often vague and non-technical, right?
Yeah, exactly. Like someone saying, I want a car that handles well and is cheap to maintain.
So the first critical translation happens when we move from the customer domain into the functional domain.
Here, we must convert those vague attributes into precise functional requirements, or FRs. Handles well is useless to an engineer.
It has to be translated into specific lateral acceleration targets, steering ratio responses, and suspension articulation metrics.
Right. The functional domain defines what the system must achieve in the abstract physics space. The next translation takes us from the functional domain into the physical domain.
Where we select specific design parameters, or DPs.
Yes, these are the actual physical variables, mechanisms, or materials chosen to satisfy the functional requirements.
So to satisfy the lateral acceleration FR, our DP might be a double wishbone suspension architecture with a specific roll center height.
Exactly. And finally, we translate from the physical domain to the process domain, establishing the process variables.
Which are the specific manufacturing techniques, like CNC milling or injection molding, required to actually manifest the design parameters in reality.
You've got it. Now, the core mechanism of axiomatic design happens at the boundary between the functional domain and the physical domain.
This brings us to Axiom 1, the independence axiom.
Yes. The formal definition states that we must maintain the independence of the functional requirements.
So in practical terms, when I select a physical design parameter to solve one functional requirement, it must not interfere with any other functional requirement.
This is where we introduce the mathematics of the design matrix. We can represent the relationship between the functional vector and the physical vector using linear algebra.
Okay, let's visualize this. If we have three functional requirements, FR1, FR2, and FR3, and we choose three corresponding design parameters, DP1, DP2, and DP3, we map their interactions on a grid.
Right. And if the design perfectly satisfies the independence axiom, we achieve an uncoupled design represented mathematically by a diagonal matrix.
In a diagonal matrix, DP1 affects only FR1, DP2 affects only FR2, DP3 affects only FR3. All other intersection points are 0.
This is the holy grail of engineering. It means you can adjust, optimize, or repair any single function of the system without initiating a cascade of unintended consequences.
But engineering rarely hands you a perfectly uncoupled diagonal matrix. What happens when our design parameters start stepping on each other's toes?
We enter the territory of the decoupled design, which yields a triangular matrix.
Imagine DP1 affects FR1, which is intended, but DP1 also exerts an influence on FR2.
Furthermore, DP2 affects FR2, but also influences FR3. This design is not perfectly independent, but it is solvable.
The catch is that it requires strict sequential execution.
Right. Yes. You must set and lock in the value of DP1 first, because it will skew FR2. Only after DP1 is finalized can you adjust DP2 to simultaneously satisfy FR2 and correct the skew introduced by DP1.
It's a fragile equilibrium, but if the sequence is rigidly documented and followed, the design is valid.
Exactly. But the nightmare scenario, the mathematical proof of a bad design, is the coupled design.
This results in a full matrix where everything interacts with everything. DP1 affects FR1, FR2, and FR3.
DP2 affects all three. DP3 affects all three.
So if you discover during testing that FR2 isn't meeting its target, you try to adjust DP2. But because it's a full matrix, turning the knob on DP2 instantly ruins the calibration of FR1 and FR3.
So you try to adjust DP1 to fix FR1, which promptly ruins FR2 again. You are locked in an infinite loop of calibration.
Just endlessly chasing a stable state that mathematically cannot exist.
Right. But wait, let me anticipate a pushback here, because it's a common one.
Okay, here's where it gets really interesting. Let me challenge the entire premise of the independence axiom.
Let's hear it.
If every function is completely mathematically isolated from every other function, haven't we just designed a box of unrelated parts?
That's the pushback.
I mean, a modern automobile is a masterpiece specifically because of integration. The engine block acts as a stressed member of the chassis, contributing to structural rigidity while also housing the combustion process.
Right.
If I apply the independence axiom strictly, wouldn't I need a completely separate chassis structure and a completely isolated engine block, adding massive weight and cost?
What's fascinating here is that this is the most common and critical misunderstanding of Sue's work.
Really? How so?
The independence axiom explicitly targets the independence of functions, not the physical separation of parts.
Oh, I see.
The rule is that the number of functional requirements must equal the number of design parameters. But a design parameter is a controllable physical variable, not necessarily a discrete physical component.
Okay, so physical integration is actually highly desirable for reducing mass, part count, and manufacturing complexity.
Exactly. Your engine block example is perfect. The block physically integrates the cylinders, the cooling water jackets, and the structural mounting points. It is one piece of cast aluminum.
However, functionally, the parameters remain independent.
Yes. The diameter of the cylinder bore, which controls combustion displacement, can be machined without altering the location of the external mounting bosses, which control structural integration.
So you have achieved physical integration while maintaining an uncoupled or decoupled design matrix.
Right. Functional coupling only occurs when adjusting the physical variable of one function inextricably destroys the physical variable of another.
Like, if boring out the cylinder wall inherently compromised the structural integrity of the mounting boss to the point of failure, then you would have a coupled design.
Exactly. So to avoid that coupling, we can't just brainstorm all our requirements and all our parts simultaneously.
Because the human brain would immediately satisfice and create a coupled mess.
Yes. The methodology demands a process called zigzagging. We don't just march linearly from the functional domain to the physical domain. We bounce back and forth.
Zigzagging is basically the disciplined application of top-down decomposition using the matrix, right?
Right. You define the highest level FR first, let's say transport payload across water. You zigzag to the physical domain and select a high-level DP, for instance, a displacement hull.
But you do not immediately try to design the propeller or the rudder.
No, you zigzag back to the functional domain and decompose the original FR into sub-requirements specifically dictated by the choice of a displacement hull.
So sub-FR1 might be maintain buoyancy, sub-FR2 generate forward thrust, sub-FR3 control yaw.
Then you zigzag back to the physical domain to select specific DPs for those sub-level FRs, a watertight volume, a marine diesel engine, a rudder blade.
By zigzagging, you continuously check for coupling at each hierarchical level before descending into the complex details of the subsystem.
Exactly. And this highlights the critical distinction between the design matrix, the DM, derived from axiomatic design, and the design structure matrix, the DSM, which is widely used in complex systems architecture.
They sound identical, but they represent entirely different philosophies of dealing with complexity.
They really do. The design matrix is fundamentally prescriptive and preventative. It demands that you engineer the system to avoid functional coupling before the architecture is locked in.
It's a tool for finding the mathematically optimal uncoupled state.
Right. The design structure matrix, the DSM, is primarily descriptive and diagnostic.
Because the DSM acknowledges that in truly massive architectures, like a commercial airliner or a global telecommunications network, perfect functional independence is often practically impossible.
Yeah, due to legacy constraints, packaging limits, or extreme physical proximity. The DSM maps the existing or inevitable coupling.
It takes the full matrix and uses clustering algorithms to identify tightly coupled nodes.
And the goal of the DSM isn't to eliminate coupling entirely, but to cluster the highly coupled elements into self-contained modules.
So you accept that the internal components of a jet engine are inextricably coupled, so you draw a hard modular boundary around the engine?
Ensuring that its external interfaces with the wing and fuel system remain uncoupled. The DM cures the disease. The DSM manages the chronic condition through quarantine.
That's a great way to put it. Okay, so once we have navigated the matrices and achieved an uncoupled design, we face Nampiusu's second profound law, Axiom 2, the information axiom.
Yes. It states that among all designs that satisfy the independence axiom, the best design is the one that minimizes the information content.
The terminology here can be deceiving for listeners, though. Information content doesn't mean the number of pages in the manual or the size of the CAD file.
No, not at all. It is rooted in Claude Shannon's information theory.
Exactly. Information, in this thermodynamic and mathematical sense, is a measure of uncertainty.
Axiom 2 dictates that we must minimize the probability of failure. The mathematical definition states that the information content, represented by I, equals the negative log base 2 of the probability of success, P.
So I equals negative log base 2 of P. That formulation is profound. But let's break that math down so it's not just an abstract equation. Why log base 2?
Log base 2 is used because information is fundamentally measured in bits binary digits, representing a choice between two states, success or failure.
Okay, so if a system has a 100% probability of meeting its requirement, the probability P is 1.
Right, and the log base 2 of 1 is 0. Therefore, the information content is 0. The system requires no additional information to succeed.
No extra control systems, no extreme manufacturing precision, no constant human intervention. It just inherently works.
But as the probability of success drops, let's say, to 50% or 0.5, the negative log base 2 of 0.5 is 1. The information content increases to 1 bit.
And as P approaches 0, the information content approaches infinity.
Exactly. A design with high information content is a design that is fighting against nature. It requires massive amounts of external energy, tight tolerances, and complex feedback loops just to keep it within the acceptable range.
The source material provides a brilliant, grounded example of the information axiom using the process of buying a house.
Oh, I love this example. It makes it so clear.
Right. So we establish our functional requirements. FR1 is a commute time between 15 and 30 minutes. FR2 is a school district where greater than 65% of high school graduates attend college.
FR3 is excellent air quality for at least 340 days a year. And FR4 is a purchase price strictly under $650,000.
These define our design range, what we are demanding from the system.
When you look at the physical options the house is on the market, you're examining the system range, which is what the physical reality can actually deliver.
And Axiom 2 mathematically evaluates the overlap between your design range and the system range.
Right. Let's look at House A regarding the commute time FR. The house is located near a major unpredictable highway.
So the actual commute time fluctuates wildly between 10 minutes on a Sunday and 60 minutes during rush hour.
The system range is wide and only partially overlaps your required 15 to 30-minute design range. The probability P of hitting your target on any given Tuesday is low, perhaps 20%.
Therefore, the information content is high. You would need to add information to the system to make it work, like leaving the house at 4 a.m. or buying expensive real-time traffic routing software.
Contrast that with House B, which is located exactly 4 miles from your office via a quiet back road.
The commute is a rock-solid 20 minutes every single day, varying by maybe 2 minutes for a red light.
The system range is incredibly tight and falls dead center inside your 15 to 30-minute design range. The probability of success is virtually 100%.
The information content is 0. Axiom 2 proves that House B is the objectively superior design parameter for that specific functional requirement because it minimizes the uncertainty of the system.
It's just brilliant. So we have our perfectly uncoupled matrix. We have minimized our information content. The theoretical architecture is flawless.
But a CAD model doesn't fly, and a blueprint doesn't pump water. We have to send this immaculate design down to the messy, imperfect reality of the factory floor.
And this transition is where brilliant engineering often turns into catastrophic failure.
Which brings us to the art of critical parameter management, or CPM.
Right. CPM is the rigorous methodology that protects the physics of your design from the economics of manufacturing.
Because the core vulnerability in transitioning from engineering to production lies in the semantic and conceptual gap between a critical parameter and a critical specification.
They are entirely different domains of reality.
This is the crux of the issue. A critical parameter is the invisible functional variable that actually dictates the physics, the chemistry, or the thermodynamics of the system.
It is the torque, the flow rate, the magnetic flux, the thermal dissipation coefficient. It is what makes the design work.
While a critical specification is the geometric dimension, the material callout, or the surface finish that actually gets printed on the manufacturing drawing.
It is the physical manifestation that the machinist or the purchasing agent actually interacts with.
And the catastrophic disconnect occurs because the downstream manufacturing and procurement teams are incentivized entirely by the critical specifications, not the critical parameters.
Right. They are tasked with making the geometric shape as cheaply and efficiently as possible. They cannot see the physics, they only see the metal.
And if they alter a specification to save a fraction of a cent, they can inadvertently destroy the critical parameter,
Rendering the perfectly uncoupled design completely non-functional in the real world, just like that jet engine spring.
Exactly. To understand why manufacturing is so obsessively fixated on geometric specifications and physical tolerances, we actually need to look back at the history of industrialization first.
Yeah. The source traces this paradigm shift back to 1765 and General Jean-Baptiste Gribeauval of the French artillery.
Before Gribeauval, every musket was a bespoke piece of art. If a trigger broke on the battlefield, the weapon was useless because a trigger from another musket wouldn't fit.
So Gribeauval introduced the concept of interchangeable parts driven by strict physical tolerances and go-no-go gauging.
Which was revolutionary for logistics, but it embedded a deep philosophical bias into Western engineering.
The belief that quality is entirely defined by strict adherence to tight physical boundaries. You design the perfect part, You draw a tight tolerance box around it, and you command the factory to stay inside the box.
And in the 1920s, Walter Shewhart at Bell Labs refined this by studying variation. He recognized that no manufacturing process is perfect.
Right. He delineated between common cause variation, the natural, unavoidable background noise of the machine, and assignable cause variation.
Things like a dull drill bit or a power fluctuation, which can be identified and eliminated.
Exactly. And the Western obsession with the tolerance box remained absolute until Dr. Junichi Taguchi introduced a profound paradigm shift.
There is a fascinating anecdote in the text about Taguchi meeting with Don Clausing, a prominent American advocate for robust design.
Oh, this story is great. Clausing, representing the traditional Western mindset, summarized the process by saying, first we do robust design, and then we put tolerances on the drawings.
And Taguchi simply looked at him and said no.
Clausing tried to rephrase, assuming a translation error, but Taguchi repeatedly shot him down. Taguchi rejected the very premise of the tolerance box.
Because Taguchi recognized that the traditional gonna-go tolerance paradigm is economically and physically flawed.
Yes, the traditional view assumes that as long as a manufactured part falls just barely inside the tolerance limit, it is 100% good.
And the moment it crosses the line by a micron, it is 100% bad, creating a step function of quality.
But Taguchi proved that quality is not a step function. It is a quadratic parabola. He introduced the Taguchi loss function,
which is defined mathematically as L equals K times the quantity Y minus M squared.
Let's break that down. L is the financial loss to society, Y is the actual measured value of the part, M is the target mean, and K is a constant translating deviation into currency.
This changes everything. It means that any deviation from the absolute dead center target mean, even if the part is technically within the engineering tolerances, degrades the performance of the system and inflicts a financial loss.
Right. If the target diameter of a shaft is 10 millimeters and the tolerance is plus or minus 1 millimeter, a shaft that measures 10.9 millimeters is legally good under the old system.
But Taguchi points out that the 10.9 millimeter shaft will cause slightly more vibration, which wears out the bearing slightly faster.
Which forces the customer to replace the bearing a year earlier than expected, damaging the brand reputation and causing financial loss.
Therefore, Taguchi argued that putting tight tolerances on a drawing doesn't create quality. It just drives up the upfront cost of manufacturing as the factory struggles to stay inside arbitrary limits.
True critical parameter management is an economic optimization puzzle. It demands that we calculate the total cost by balancing two opposing financial forces.
The upfront cost of buying higher manufacturing precision versus the long-term financial quality loss incurred by allowing variation in the field.
The text calls this the customer tolerance, or delta C.
Right. It defines the specific threshold of variation where the physical degradation of the product finally triggers an unacceptable financial consequence.
Like the point where the customer gets so frustrated they demand a warranty replacement, or an aircraft is grounded for unscheduled maintenance.
So we must optimize our manufacturing processes against that financial delta C, not just against a geometric ideal.
Let's ground this with the paper feeder example from the source data. Imagine designing the paper handling mechanism for a commercial printing press.
Okay, through axiomatic design and physics modeling, the engineering team determines that the critical parameter is exactly 15 newtons of belt tension.
That invisible force required to strip a single sheet of paper without jamming. That 15 newtons is the absolute target mean.
However, 15 newtons cannot be manufactured. It must be assembled.
Exactly. The manufacturing drawings contain the critical specifications: the diameter of the drive roller, the durometer of the rubber belt, the geometric mounting coordinates of the tensioner arm, and the spring constant of the coil spring.
This is where tolerance stack-up analysis becomes terrifying. Every single one of those critical specifications has its own natural manufacturing variation.
The roller might be a fraction of a millimeter too small. The spring might be slightly too stiff.
If all those variations randomly align in the same direction, a worst-case scenario, the resulting physical assembly won't produce 15 newtons of tension.
It might produce 11 newtons, resulting in constant paper jams, or 19 newtons, which shreds the paper.
And if a procurement agent, ignorant of the 15-newton critical parameter, decides to source a cheaper tensioning spring,
even if it meets the basic dimensional specifications, but possesses a wider variation in its spring constant, they save a few cents on the bill of materials.
But they have fundamentally altered the statistical distribution of the output tension. The 15 newtons is lost in the noise.
The Taguchi loss function activates exponentially. The printing presses fail in the field, production stops, warranty claims skyrocket.
And millions of dollars are lost because the organization managed the geometric specifications instead of managing the critical parameter.
Exactly. The source provides another stark example of this total cost optimization. The decision between turning and grinding a metal shaft.
Let's say we need a 25 mm shaft. We can manufacture it using a lathe, a process called turning, which yields a natural precision of 0.05 millimeters.
Alternatively, we can use a cylindrical grinder, which achieves a much tighter precision of 0.01 millimeters, but operating the grinder costs 3 times as much per hour.
The old paradigm would simply ask the design engineer what tolerance they want.
And the engineer, wanting to be safe, would demand the 0.01 millimeter tolerance, forcing the use of the expensive grinder and driving up the cost of the product needlessly.
But critical parameter management forces a systemic financial calculation. We apply the Taguchi loss function.
We ask, what is the actual financial damage caused by a 0.05 millimeter variance out in the real world? Does that extra 0.04 millimeters of slop cause the gearbox to fail before the warranty expires?
If the financial loss caused by the looser turning process is negligible, meaning it doesn't cross the customer tolerance delta C, then paying triple for the grinding process is engineering malpractice.
We optimize for the total economic economy, not the tightest possible geometry.
So we have mapped the physics, we have optimized the total economic cost, and we know exactly what target mean we need the factory floor to hit.
But how do we mathematically prove that the factory is actually capable of hitting it, day after day, across tens of thousands of units?
This brings us to the ultimate crucible of systems engineering: capability indices and the 7 checks for criticality.
To answer the question of capability, we must transition into the mathematics of statistical process control. We rely on 2 fundamental capability indices, CP and CPK.
These metrics are the bridge between the theoretical design limits and the stark statistical reality of the manufacturing machine.
To understand them, we must briefly establish the concept of standard deviation, represented by the Greek letter sigma.
Sigma is a measurement of the dispersion or spread of data around a mean. In a normal distribution, roughly 99.7% of all data points fall within plus or minus 3 sigma from the center.
Therefore, a 6 sigma spread encompasses virtually the entire natural variation of a manufacturing process.
Let's derive CP first. CP is the short-term capability performance potential.
It asks a very simple geometric question. Is the natural variation of the machine physically narrow enough to fit inside the allowable tolerance window dictated by the design?
The formula for CP is a ratio. We take the tolerance width, which is the upper specification limit, minus the lower specification limit, and we divide it by the natural process variation, which is 6 sigma.
If our tolerance window is wide and the machine's 6 sigma variation is very tight, we get a CP value greater than 1. A CP of 1.33 or 1.67 indicates a highly capable process potential.
However, CP measures pure potential, completely oblivious to reality.
Right. CP only compares the width of the process to the width of the tolerance. It assumes the process is perfectly centered on the target mean.
But machines drift, tools wear down, thermal expansion shifts fixtures.
If a highly precise machine is operating off-center, it might be churning out perfectly consistent parts that are entirely out of specification.
This is why we must calculate CPK, which represents the actual observed capability, accounting for any shifts in the mean.
The formula for CPK forces us to look at the boundaries. We calculate the distance from our actual operating mean down to the lower specification limit, and we calculate the distance from the upper specification limit down to our mean.
We take the smaller of those two numbers because that represents the side where we are closest to failure, and we divide it by 3 sigma, representing half of the process variation.
To crystallize the difference between CP and CPK, we can use the analogy of driving a vehicle into a parking garage.
Oh, this is a great visual. The parking space, defined by the painted white lines, represents your tolerance width.
And the physical width of your car represents the natural 6 sigma variation of your manufacturing process.
So calculating CP is simply asking, is my car physically narrower than the parking space?
Exactly. If you are driving a compact car and attempting to park in an oversized RV space, your CP ratio is fantastic. You possess the theoretical potential to park without crossing the lines.
I have the potential to park, but CPK is the brutal reality check of how I actually parked.
Precisely. You might have a compact car and a massive space, granting you a great CP. But if you execute the maneuver poorly, parking the car extremely off-center.
With your left tires resting directly on the painted line and dangerously close to a concrete pillar.
Right, then your CPK will be abysmal. The calculation looks at the minimum distance to the limit. Because you're on the line, that distance is 0.
So your CPK is 0, indicating an unacceptable risk of failure, a scratched door, despite having the potential for a perfect outcome. But let me push back on the necessity of calculating both metrics.
Sure, do it.
If CPK tells me the actual reality of where the car is parked and whether I'm about to hit the pillar, why do I even care about CP? Isn't CP just a theoretical fantasy?
Because separating potential from reality provides the fundamental diagnostic intelligence required to fix the process.
Oh, I see.
If your manufacturing line is producing defects, you need to know if it's a capital expenditure problem or an operational calibration problem.
So if you calculate CP and it is less than 1.0, it means your car is physically wider than the parking space.
The underlying technology of the machine is fundamentally incapable of holding the required tolerance. No amount of careful calibration or operator training will fix it.
You must spend capital to buy a fundamentally more precise machine, or you must go back to the systems engineers and demand they widen the tolerance window.
But if the CP is good, and only the CPK is bad,
then you are in a highly salvageable situation.
exactly. If CP is 1.67, proving the machine is incredibly precise, but CPK is 0.5, proving you are producing defects, it simply means you parked the compact car on the line.
The process is just shifted. You don't need a new $1 million CNC machine.
You just need the operator to adjust the tool offset, recenter the mean, and your CPK will immediately rise to match your CP. Calculating both indices prevents organizations from throwing away capable machinery out of ignorance.
This mathematical foundation is the prerequisite for the final gauntlet, the 7 checks for criticality.
Every single critical parameter identified during the systems engineering phase must survive these 7 sequential checks before the design can be validated for mass production.
Let's walk through these checks, not just as a list, but as a diagnostic protocol, perhaps using a critical component like the cooling channels inside our jet engine turbine blade.
Perfect. Check number 1. Is the parameter measurable? This sounds trivial, but it is the graveyard of many advanced designs.
If the critical parameter is the internal surface roughness of a microcooling channel deep inside a cast titanium turbine blade, and you physically cannot insert a probe or use non-destructive imaging to measure it accurately,
You have no data. If you can't measure it, you can't calculate a mean or a standard deviation. You are flying blind, relying entirely on hope.
the engineering term for this is establishing gauge R&R repeatability and reproducibility. The measurement system itself must be proven statistically sound before you even measure the part.
Assuming we develop a laser interferometry technique to measure it, we move to check 2. Is the parameter stable?
We put the measurement data on a control chart over time. Is the mean diameter of the cooling channel wandering aimlessly hour by hour?
Stability proves that all assignable causes of variation, like a fluctuating power supply to the casting furnace or a degrading ceramic core, have been identified and eliminated.
If the process isn't stable, you cannot predict its future performance, rendering any capability calculation mathematically invalid.
Once stable, we face check 3. Is it adjustable?
If our CPK reveals that the mean diameter of our cooling channel is drifting too close to the lower specification limit, do we have a specific operational lever we can pull to recenter it?
Can we adjust the firing temperature of the furnace or modify the pressure of the wax injection? If the parameter is a locked artifact of a complex chemical reaction with no external controls, we are paralyzed.
Check 4 forces us to look back at axiomatic design. Is the parameter interactive?
If we pull that lever, if we adjust the furnace temperature to fix the coolant channel diameter, do we inadvertently alter the crystalline structure of the titanium alloy, destroying the blade's tensile strength?
If the parameter is highly coupled, adjusting the mean will initiate that catastrophic loop of compromises we discussed earlier.
Check 5. Is it sensitive? How fiercely does the critical parameter react to changes in the manufacturing environment that we cannot easily control?
If a 10-degree shift in the ambient humidity of the factory floor causes a massive dimensional swing in the wax molds used for the turbine blades, the parameter is overly sensitive.
We must formulate the process to be immune to that background noise.
Which feeds directly into check 6. Is it robust?
A robust parameter, in the Taguchi sense, is one where the functional output remains absolutely constant despite variations in the input factors and environmental noise.
We want a high signal-to-noise ratio. The intended function dominates the parasitic interference.
And finally, check 7. Is it capable? This is the mathematical verdict.
Have we calculated the CP and CPK using rigorous, statistically significant data samples?
And do the indices prove that the manufacturing process can consistently deliver the critical parameter within the customer tolerance delta C, ensuring the overall economy of the system?
If a parameter survives all 7 checks, it is no longer a theoretical geometry on a CAD screen. It is a validated physical reality ready to scale.
And the incredible thing about capability is that it isn't a static snapshot. It is a living metric.
We tend to assume that everything degrades over time. Tooling wears out, bearings introduce chatter, the CPK inevitably drops.
While entropy is real, a mature systems engineering organization can actively reverse it through a process called capability maturation.
Capability maturation is the hallmark of an advanced enterprise.
By continuously monitoring the CP and CPK metrics across the entire product lifecycle, from early prototype builds through low-rate initial production and into full-scale manufacturing, the engineering teams can identify subtle, long-term trends in the variance.
By systematically eliminating microsources of noise and refining the process variables, the CP and CPK indices can actually grow,
resulting in a product that becomes statistically more perfect and economically more profitable the longer it is manufactured.
It is the ultimate feedback loop. We start by acknowledging the cognitive limitations of the human brain.
We deploy the systems engineering V model and strict requirement semantics to debias our organizational decision-making.
We apply axiomatic design to mathematically decouple our physical variables from our functional demands, minimizing the thermodynamic information content.
We use critical parameter management to protect the physics from the economics.
And we relentlessly execute the 7 checks to mathematically guarantee our capability. It is a breathtaking architecture of logic.
It is the invisible infrastructure of the modern world. But it leaves us with a profound, almost existential question regarding the future of the discipline.
Yeah, we have established that this entire elaborate architecture, the decomposition, the zigzagging, the strict avoidance of coupled matrices, exists primarily because human working memory cannot process massive, intertwined complexity.
We must isolate variables to understand them. But we are now entering the era of artificial intelligence.
The implications of that for axiomatic design are staggering.
If a specialized generative AI system possesses an effectively infinite working memory, it does not suffer from cognitive overload. It does not satisfy.
Therefore, we must ask, will AI eventually be capable of successfully navigating and optimizing a massively coupled design?
Could an AI safely manage a full chaotic design matrix where millions of variables interact simultaneously, achieving levels of physical integration and efficiency that human engineers could never safely attempt?
Or, conversely, are non-POSU's axioms the absolute demand for functional independence and the minimization of information content, not merely cognitive crutches for flawed humans?
Right. Are they fundamental, unbreakable laws of the physical universe that even a supercomputer must obey to avoid catastrophic failure?
It is the question that will dictate the trajectory of engineering in the 21st century.
That's going to be fascinating to watch it unfold.
Whether AI breaks the matrix or confirms the axioms, the fundamental laws of critical parameters will remain. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.